Let's look at this is AB Exam Review Worksheet 3. Number 1 is an optimization problem. It says rectangular area is to be enclosed by a wall on one side and fencing on the other three sides. So here's the wall, and we have two sides that are parallel forming the rectangle, and then we have vertical. I'm going to call this the Y value. 18 meters of fencing are used. What's the maximum area that can be enclosed? We know that we're dealing with optimization, so the steps that we take is we identify the equation we're going to be optimizing. So we're going to be working with the perimeter and the area equation. So area is length times width, so xy. Perimeter is 2x plus y, so we're just dealing with three sides, so 2x plus y. And we know it's equal to 18, so y is equal to 18 minus 2x once we solve for y. Now when we solve for y, we can then plug into the area equation, because in the problem we're trying to maximize the area that can be enclosed. So we're trying to optimize area, so we're trying to find the derivative for the area equation, but we need to get the area down to one variable on the right side, so we can use the perimeter equation to help us get there. So 18 minus 2x replaces y. Then we can expand, and then we can find the derivative. So 18x becomes 18. 2x squared becomes negative 4x. We solve for x. X becomes 9 over 2. So if we know that the optimal length for x will be 9 halves. And if we want to find the area using this optimal length, then we plug 9 halves into the area equation. So 18 times 9 halves minus 2 times 9 halves quantity squared gives us 81 over 2 square meters. Right, number 2, we have a slope field question here. What we're trying to do is we're trying to match the slope field with the correct differential equation. Now remember, when we're looking at the slope field, each of these slope segments represents the slope of the tangent line for a particular graph. So what we can do is rather than testing out every ordered pair and seeing which one is correct, if we can identify some common patterns or some general patterns, then we can use those pattern characteristics to help us narrow down our choices. Okay, so one thing that that we notice here is that even though we may be able to look at the slope field and identify whether it's a negative slope at this order pair or a positive slope, we may not know exactly for sure. But the ones that we do know for sure are where slope is 0. So if we look at the slope field here, we can see that slope is 0. We see the horizontal line segments right along the y-axis, and the y-axis. So what that means is that whenever something is on the y-axis, this also means when x is 0. So basically, whenever x is 0, we know that the slope must be equal to 0. That the differential equation's value will give us 0 when x is 0, because we see that on the slope field. Several other general traits that we can identify here is that if we look at the quadrants, we can see some general patterns as well. Right? Notice the first quadrant, everything you see here is positive slope. In the second quadrant, these are all negative slopes. Third quadrant, positive slope. Fourth quadrant, negative slope. So we have some general characteristics which will help us narrow down our choices here. We know that first and third quadrant will produce positive slope values, positive derivatives, and second and fourth quadrant will produce negative slopes. So let's go down our answers here. We know that we must get 0 when x is 0, because we see that on the graph. So if I plug 0 in for x, I don't get exactly 0 for part A, because if I plug in 0 for x, I get 0 times y minus y. Negative y is not going to always be equal to 0, so we know this one is out. Okay, dy dx equals 4. Well, when x is 0, there's no x to plug in, so this is saying that this differential equation always has a slope of 4, and we can tell by looking at this slope field that we have all these slope segments that have all different slopes. These are not a constant value of 4, so we know this can't be it. 3y squared minus 4. Okay, there's no x values to plug in, so we know that the derivative is not always going to be 0 when x is 0, because when x is 0, this is completely dependent on the y value, so we know this can't be it. Okay, dy dx equals x times y. Right? If I plug 0 in for x, I get 0, so looks like that matches, right? Let's look at part E as well, choice E. Choice E, 5 times 0 is also 0, so looks like we're down to 2 choices here. So this characteristic alone is helpful in the sense that it eliminated the first 3, but this one is not enough to help us differentiate between the last 2 answer choices. So we're going to use this to help us out. We know that any ordered pair in the first and third quadrant must give us a positive slope. So let's test this one. Let's choose an ordered pair here. We know that 2, 2, for instance, must give us a derivative of a positive value. So if I plug 2, 2 in, 2 times 2 is 4. That's a positive slope, so that's true. If I plug in 2, 2, I get 5 times 2, and that's 10. That's positive slope. Okay, so that looks like we're still not able to differentiate. Let's try the second quadrant. So second quadrant, negative 2, 1, for instance. Negative 2, 1 must give us a negative slope. So if I plug negative 2 in for x and positive 1 for y, negative 2 times 1 is going to be negative 2, so that gives me a negative slope. Negative 2, 1 also gives me negative slope, so that doesn't help me out either. If I try the third quadrant, anything in the third quadrant must give me a positive slope. So if I plug negative 1, negative 1, negative 1 times negative 1 is positive 1, so that's positive slope. Negative 1, positive 1, if I plug negative 1 in for x, there's nothing to plug in for y, it gives me a negative slope. So therefore, I know this is out. Must be answer choice D. All right, for E, we have y is equal to natural log of e to the x over e to the x minus 10. Find dy dx. So if we want to find dy dx, we need to find the derivative. But this is a problem where we want to take advantage of the fact that this is a log expression, which means that if we can expand log expressions first, that will help ease having to take a derivative of a function that could be too complex to begin with. So if we did jump directly into the derivative rule, which is u prime over u prime will require us to have to go through quotient rule, and that's going to be a bit messy. So if we can expand the expression first, then it'll make the next step with derivative a lot easier to work with. So notice that this is in the form of ln of a over b, so which means that I can use the quotient property to expand this log expression. So natural log of a over b is natural log of a minus natural log of b, right? So using that property, I can say natural log of e to the x minus natural log of e to the x minus 10, and then and I can keep expanding because this x can come down in front using the power property. So if I bring the x down in front, x times natural log of e is just going to be x times 1. So x minus natural log of e to the x minus 10. Now if I go to the, this derivative of this problem is going to be a lot easier to work with than this, because I've expanded this into smaller portions, and then I can just find the derivative of each individual portion. So now let's find the derivative. The derivative for x, just go power rule, x becomes 1. Natural log of e to the x minus 10. Now I can go through the derivative rule for natural log of u, which is u prime over u. So u prime is just e to the x minus 0, or just e to the x, over the u value, which is e to the x minus 10. And this is essentially my derivative, but I have to match with one of these answer choices. So it looks like if we can find a common denominator, we should be able to match. So common denominator is e to the x minus 10. I can balance the 1 by writing it as e to the x minus 10 over e to the x minus 10. So e to the x minus 10 minus e to the x. The e to the x cancels out. We're left with negative 10 over e to the x minus 10. And if I multiply top and bottom by negative 1, then I can make this 10 over 10 minus e to the x, which matches answer choice C. Last one on this page is also an expansion problem. If we try to go directly into the derivative rule for natural log of u, u prime is going to be a little messy, having to go through potentially product and chain rule. So if we can expand using expand using not power property, but then also product property, we can say we can let this represent the a and let the square root represent the b. And if that's the case, we can say natural log of a times b is equal to natural log of a plus natural log of b. So we can split this up as natural log of x plus natural log of square root of x squared plus 1. And I can rewrite the square root of x squared plus 1 as a rational exponent, natural log of square root of x squared plus 1 to the 1/2. Now using power property, not derivative rule, we're just expanding here. We can take exponents and bring it down to the front. This is nothing to do with derivative. This is just simply using the power property for natural logs or for logs. Now this is going to be a lot easier for us to find the derivative for. So we've split this up into two smaller problems. Natural log of x, the derivative is u prime over u, or 1 over x. The derivative for natural log of x squared plus 1, the u value is x squared plus 1, so u prime is 2x over x squared plus 1. Multiply the 2 through, the 2 cancels out, and then we can find a common denominator at this point. And we get x squared plus 1 plus x squared, x squared plus 1 plus x over x times x squared plus 1, so this matches answer choice E.